Welcome to the lecture 7 part A. In this lecture we are going to talk about multicollinearity. We consider the linear model y equal to x beta plus epsilon, where epsilon follow normal distribution 0 sigma square in and n is greater than p. So that means sample size is greater than number of features that we have in our data set. Okay. Now, if this is the case, then we can show that y follow normal x beta sigma square in. Okay, it's an invariant normal. The least square estimator of beta will be beta hat, which is x transpose x inverse x transpose y. Now, in the previous lecture we also discussed that beta hat follow p-variate normal with mean as expectation of beta hat as mean as beta, and variance of beta hat is sigma square x transpose x inverse. Now, first question we will ask ourselves that what is multicollinearity? If correlation between two predictors, so there are p many predictors, so x is typically x1 to xp, okay, if any of the two predictors have correlation exactly 1. So correlation between say ith predictor and the jth predictor is exactly 1. That means one column is exactly dependent on other, and that will result determinant of x transpose x to be 0. So it immediately means that x transpose x is not invertible. Because what is x transpose x? X transpose x is x transpose x inverse is adjugate of x transpose x divided by determinant of x transpose x, and if it is 0, so that means x transpose x is not invertible. In such case, unique solution does not exist, right? Now, in such situation, now this is what I am giving you a extreme situation. Okay, now most of the time you will never probably put one, if one column is exactly linearly dependent on other, so that means effectively you can write xi equal to some constant of xj, right? So and if we know that there are some columns which is exactly linearly dependent on another column, then we will not put that column in our data set at all. So this is an extreme example. More reliable, more reasonable example is that correlation between two predictors nearly 1 or minus 1, but not exactly 1. It will not be exactly 1. So correlation between say xi and xj is 0.99. What happens then? So in that case, what will happen is determinant of x transpose x is some small delta value where delta is positive. So determinant of x transpose x will be very small value. Delta is a very small value. Okay, it's a very small value. So x transpose x will be invertible. There will be no problem. X transpose x will be invertible. But every element of x transpose x will be very large. Every element, because what is x transpose x inverse? X transpose x inverse is adjugate of x transpose x and divided by determinant of x transpose x. Now, if x transpose x, determinant of x transpose x is very small value, then basically you are dividing every element of adjugate of X transpose X by a very small value. Effectively, that will make the every element of X transpose X inverse very large. So what will happen in this case is basically unique solution of beta hat exists, but the covariance of beta hat will be extremely large. So every element of covariance of beta hat will be extremely large. So the standard error, so naturally the standard error of beta hat will be very large. Hence valid statistical inference cannot be implemented. What does it mean actually? Let us try to understand with a simple toy example. So I'm considering a no intercept model of I'm considering the empty curves dataset. It's a small toy dataset, but very good dataset to understand the multicollinearity. I'm considering a no intercept model. Okay, just to understand the concept. I mean, probably I will not use in real I'll do a proper analysis, but just to understand the geometry of the concept, I'm using a simple no intercept model where miles per gallon is a function of weight and rear axle ratio. So MPG equal to beta 1 weight plus beta 2 weight plus epsilon. I know correlation between weight and rear axle ratio is negative 0.71. Okay, not very bad, like 0.99 or something, but on a higher side. Now what is happening? If you estimate the beta 1 hat and beta 2 hat, OLS estimator, correlation will be 0.92. Okay, so what is happening here? So you can see this is correlation is very high. Now what is happening is basically the correlation is whatever the correlation that you are seeing between x1 and x2 that is getting induced in the sampling distribution of beta hat. Because what is the sampling distribution of beta hat? You see, beta hat is following p-variate normal. In this case it will be p-variate 2-variate normal with beta sigma square X transpose X inverse. Now correlation between the weight and rear axle ratio, this will get reflected in the correlation between the two, of course adjusted with for sigma square. But this, as a result, because the high correlation, the whole thing become very large, and as a result what is happening is, if you do a 95% confidence interval, see, beta 1 was the correlation, beta 1 was coefficient of weight. Okay, now it becomes so big, it includes the confidence interval includes the 0. So based on our statistical inference will say that beta 1 does not include 0 is possible value of beta 1, so weight does not have effect on MPG. So weight does not have impact on MPG. Okay. Now instead of OLS estimator, if we use the Ridge estimator, what happens is, Ridge estimator, we will talk about it, how Ridge estimator is being calculated. The correlation between Ridge estimator is reduced to negative 0.73. The correlation between the OLS estimator was very high, negative 0.92, and as a result it was getting very tight. Now ridge estimator reduced the correlation, so that means this tightness is now reduced. It is now here. Now the confidence interval does not include 0 anymore. So using ridge estimator, we can say, using ridge estimator, we can say that beta 1 is non-zero, that is, weight do have effect on MPG. Okay. So I hope the concept of the multicollinearity is clear now. So because of the, in summary, we can say that because of the extreme correlation between the predictors, that correlation between the predictor get induced in the sampling distribution of the OLS estimator. As a result, the sampling distribution become very tight, and as a result the standard error or the margin of error for each estimator become very large. So the standard error or margin of error get inflated, and we cannot do a proper statistical inference with such kind of estimators. But we have to do that, means some correction, and ridge estimator is one such correction for multicollinearity, and this problem is known as multicollinearity. Now for this kind of problem, multicollinearity problem, we have to do some kind of correction. Ridge estimator is one such estimator which actually do the correction, and because of the ridge correction, the correlation between the coefficients, the sampling distribution reduces, and as a result the overall standard error reduces. Next question is how I identify if my data suffers from multicollinearity. There are many different ways to identify. One kind of foolproof method is variance inflation factor. Variance inflation factor, VIF, is an index which indicates how much feature is contributing towards multicollinearity problem. So analyze the magnitude of the multicollinearity by considering the size of the variance inflation factor. A rule of thumb is if the variance inflation factor is greater than 10, then definitely there is a high multicollinearity. Cutoff 5 is also commonly used. Now, what is the motivation of variance inflation factor? Consider a linear regression model, y equal to x beta plus epsilon. Standard error of beta j is this. Okay. So you just take the x transpose x inverse, the jth diagonal element of the x transpose x inverse, multiply with the sample variance and take the square root of that. It turns out that the variance of beta j can be also expressed as this, that a square by n minus 1 variance of xj times 1 by 1 minus rj square. Now what is rj square? Rj square is multiple r square of xj on x1 to xj minus 1 and xj plus 1 to xp. So basically you set up a simple regression model of where dependent variable is xj and equal to gamma naught plus gamma 1 x1 plus dot 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 gamma j minus 1 xj minus 1 and gamma j plus 1 xj plus 1 to gamma p xp plus epsilon. You fit that model and can get the multiple r square for that model, and that model's rj square is this rj square. Now the term 1 minus rj square is known as the variance inflation factor of the jth predictor. Okay, so question is how we can calculate p different VIFs, one for each feature. First, we run the ordinary least square regression that has xi as a function of other explanatory variables. Say suppose if I equal to 1, we fit x1 as a function of gamma naught x plus gamma 2x2 plus dot 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 gamma pxp plus epsilon, and then you calculate the variance inflation factor. Beta I would be simply this guy 1 over 1 minus ri square. Once you have that, if it is greater than 10, you call it there is a multicollinearity. If it is greater than 5, then that is also can be used for multicollinearity. So in R, there is a function called VIF in the car package which implement the variance inflation factor. In Python, function variance inflation factor is a there is a function called variance inflation factor in stat models package that can be used to identify the multicollinearity. Next video, we will discuss issues of ill-posed problem, and the problem of multicollinearity is a special case of a class of problems called ill-posed problems. Okay, so we'll stop here and see you in the next video where we will discuss the class of ill-posed problem. Thank you. Bye.